Welcome back to DemystifySci. I'm Anastasia.
I'm Shiloh.
And this is the place where we explore the theories that we think may change the world. I say may change the world because we believe that it's really imperative to play with ideas, even if they're not necessarily correct. And scientific theories are no different than any other idea. And so this is the place where we invite people who think that they have a new way of looking at the world. We try to lay it out, we try to understand it so that we can go out and we can see, does it make sense? Does it fit with the way that we see the world? Does it help us see the world in some new and vibrant way that we didn't have beforehand? And today we have with us Dr. Patrick Vanraes, who has been studying plasma for most of his career and has come up with a model of the world that suggests that we have completely misunderstood what is the nature of plasma. Basically, the standard model says that plasma is the fourth state of matter. Every single presentation on plasma starts with that, and it says you go solid, liquid, gas, plasma. And Patrick is like, well, actually, I think that that's not correct. I think that that's a transition that is very distinct from the other three. And he lays out in this conversation that basically, in his view, almost anything can be a plasma. Is that fair?
It's a really, really nebulous idea, and that is actually something I think we have worked ourselves to an interesting conclusion for by the end of this conversation. So I think you guys probably have your own opinions, but I'm sure that we all align on this idea that plasma is a sufficiently nebulous concept that applying it to any explanation proves very, very squishy.
Well, specifically, if we're wrong about what plasmas are, if plasmas aren't just superheated ionized gases, then everything that we have to say about cosmology and about distant stars and the formation of galaxies and the history of the cosmos might actually not be correct. And so Patrick's reimagination of plasma as being kind of the capacity of matter to be conductive even in the absence of current lets us see plasma as being something that is a property of matter rather than a state change or a phase change.
I'm not going to tell you the conclusions that we come up with because I want you guys to check it out in its full glory. But if you're really into this kind of thing, remember, we are meeting this summer very, very soon in Sesimbra, Portugal. That's June 12th to 16th for our Beyond the Big Bang conference. This is really cool because Patrick is one of our presenters and he's also one of our co-organizers. So Patrick has done a fantastic job of cultivating a book of abstracts. He's helping us put together a roadmaps paper for what comes next. What do we learn from the conference? And we're going to put together our first DemystifySci laboratories paper, essentially.
Oh.
So I would love to see you out there. We have a few tickets left. There are no rooms left, but if you can get your own lodgings, we still have seats at the table. And I'd love to see you there. Also, this project in general is entirely paid for by you guys, our listeners. And so if you are already supporting this project, thank you. You're the ones who are making this possible so that we can put all of this time and energy into bringing these conversations, these conferences, all of that. If you're not yet supporting the project, but it's something you enjoy a lot, consider that for 75 cents a week, you can join our Patreon and really propel us into the future with this project. You also get a chance to hang out with us once a week, and you can tell us your ideas of what's happening in the world, what should we be checking out, and how can we do this better. So I would love to see you over at patreon.com/demystifysci.
And if you have a theory about how the world works, anything from economics, psychology, physics, chemistry, biology, consciousness, come to Paradigm Drift. We collect names all month, we put them in a hat, and then we pick names out one at a time. You get 60 seconds if you are picked to present your idea, and then we interview you afterwards with our panelist. We have some live music. It's very fun. Everybody hangs out in the chat. And so signups for Paradigm Drift are in the description. They are also right here.
This is going to be a really good one. We're going to be hanging out with my childhood friends in Ohio, and we will be playing some live guitars in between the sets. I think you guys are going to love it. So sign up for Paradigm Drift. Check out the conference if that's something you're interested in. And yeah, enjoy the conversation with Patrick. See you next time.
The scientific revolution starts now.
The Demystify Sci podcast. Learn to see in the dark.
Plasma is a absolutely critical term for the study of the cosmos. Everything from astrophysics and the way stars work to the stuff that stars are made from to the galaxy itself, this word plasma crops up. It also plays an important part in the way that we understand weather, various technologies on Earth. And that word plasma seems to be such an enormous term that it becomes almost impossible to understand which variety of that term someone is using at any given time. And so we recently had a podcast with Eric Lerner, who's going to be one of the presenters at the conference. And Eric embraces Hans Alfvén's plasma cosmology, right? But when you ask Eric what he means by plasma, it's usually something like a state of ionized gas where atoms have lost their electrons, right? And they've sort of separated. And from a material perspective of what an atom is, it's kind of hard to imagine what exactly that means. So I don't know. I was hoping that today we could just sit around and try to make sense of that term plasma and why it's so confusing and why it means almost anything. And you're a guy who's studied plasma for many years, so maybe you can help us get oriented to this term a little bit better.
Yes, I think I do. I actually wrote specifically about this topic, what is plasma, and should we maybe broaden the definition a bit or significantly. I wrote about this already basically in 2018, it started. And then in 2020, I really got serious about it. Ultimately, I still have to publish most of my ideas about it. But yeah, it's, I think, more complicated than most people think it is, especially plasma physicists. Because if you ask a plasma physicist what plasma is, very often they will say, for example, as Shiloh just said, it's an ionized gas. It's something where you have, instead of neutral particles flying around in the gas phase, you have charged particles. You have the heavy particles, which are the ions, typically positively charged, and then surrounded by the electrons, which are way lower in mass, like 10,000 times, 1,000 times lower in mass. So they're way more mobile than the positively charged cores, ionic cores that are flying around. And that's it. That's the plasma. And of course, there is a little bit more to it. You can have some other particles inside this plasma. But there are typically not too many deviations from that definition. There is, on the other hand, another definition that is also very commonly used. For example, almost every PhD defense that I went to about plasma, some plasma research, which were, I think, around 30 PhD defenses by now, all of them have this definition of plasma being the fourth state of matter. That's how they typically introduce it at one of the first slides. You have, you start with a solid. Let's, for example, take ice. You heat it up, it becomes liquid. You heat it up further, it becomes gas, so in this case, vapor. And then if you add more and more and more energy, ultimately this species, they will get, this gas species, they will get such a kinetic energy, which is comparable to the ionization energy, that at least the most energetic ones begin to ionize the particles that they fly against. If you consider them like bowling balls, that's of course a model. It's a little bit more complicated than that if you look at the quantum mechanics. But in the end, it comes down to this idea of you have in this bunch of gas particles always a section which is very energetic, which are the first to ionize the other particles. And that's how you get a plasma according to this fourth state of matter definition.
So what's the fundamental difference between that and something like a metal, where you also have the same, by the same accounting sense, you have these delocalized electrons, and you have, a rigid lattice of nuclei, I suppose. But, in some sort of conductive liquid, for instance, how do you separate that from a plasma? Because the nuclei are still moving around, and you still have the delocalized electrons.
There is a very clear similarity there. And that's, I think, where the confusion begins. Because if you go to the specialized literature, you will see that there are definitions of plasma which include a metal as a plasma. And especially if you look at the electron gas, as they call it, the electron gas in this plasma, you can model it as what they call a one-component plasma model. So the name says it already by itself. Scientists consider this to be a plasma. Why not include this into this term plasma, according to the conventional definition? And that's where I think there is this tension between a few different fields in plasma physics, which have been so isolated from each other, historically speaking, that you have the majority of plasma physicists still keeping with this very narrow definition of plasma needs to be something gaseous, versus a niche in which like a little group of researchers say, like, this is too limiting for the real definition of plasma. It's actually broader than this. You can consider this to be many more states of matter.
And this could be a problem, I suppose, because if you imagine that all of your plasmas are gaseous and they aren't, then you might end up using, say, ideal gas laws when you shouldn't, or something like that. What
Yes,
could go wrong?
I think most plasma physicists are aware of some certain non-idealities compared to an ideal gas, because ideal gases do not behave as plasmas. They are considered to be, let's say, a collection of billiard balls flowing through the air with Brownian motion and then hitting each other, and that's one model of how you can consider gas. But so these bowling balls, these molecules, these atoms, whatever is the composition of this gas, they are considered to be chargeless, neutral. And that is, of course, very, very important for how this gas behaves compared to a plasma. In a plasma, you have not only charged particles, but the charged particles in plasma make it different from the neutral gas. And that's where the story begins. Because this... Yeah.
Well, if that's so, like, why does Eddington use ideal gas laws to build up the equations of state for the stars, which then people modify over the next century or so? Like, why are they using ideal gas laws?
I guess that's how scientists work. They start with what they know and then add elements. And of course, to a certain extent, you can use ideal gas, let's say, characteristics for describing a plasma, but you have to go beyond that, certainly if you want to consider what's happening on a more microscopic scale, but also macroscopically.
Yeah, like maybe we can deal with that a little bit, which is, why does reconceiving of plasma seem necessary? Because if you can look at something like stars, which we acknowledge are made of plasma, then if the ideal gas law works, and if you have different equations that work for, let's say, what happens inside of a metal that also works, like, what is the motivating feature that requires us to start to think about plasma as being something different? What does it give us?
I think the very first realization that you have to make is ideal gas law is about typically one type of particle. And if you have a mixture of a gas, they are not going to consider the different particles as too differently, or you begin to get these extensions. For example, you have these rotational energies and vibrational energies that you can add with multi-atomic gas particles. But that's not exactly what I want to go to here. It's more that if you have a plasma, you have two very different types of particles, typically. Let's say now the gaseous plasma. You have at least some ions and electrons. And these ions are very different from the electrons. So you cannot just simply say like we have one type of gas particle that we will consider as the basis for this ideal gas law. So you need to split up your gas law, as it were, into the electrons and the ions. And then, of course, the whole thing begins to get complex because these two interact with each other.
Okay, and so when we look out onto the world, what are the pieces of the world that we miss by ignoring that plasma occurs as more than just this state of matter where you've pumped tons and tons of energy into it? Right, because I guess
What do you mean?
Well, what I mean is this. I'm like, the function of a theory, in the way that I see theories, is that they let you do something. Right? Like ideal gas law lets you treat gases in thermodynamic contexts in order to be able to do work, like in the most simple way. And so if we have a science of plasma,
Well, I think from an engineering perspective, yes, but from a scientific perspective, like your theory should help you understand what's happening.
that's true. And so I'm like, even so, from the engineering perspective, if you are trying to build something and you don't actually understand how plasma works, like what are the ways in which we need to understand different kinds of plasma in order to build them? But then further, what are the phenomena that we look at that we assume are not plasmatic that would make more sense if we treated them as plasmas? Does that make sense?
Yes. So now we're going away from the gas phase, I assume, because in general, when a gas is behaving like a plasma, then physicists will call it a plasma anyway, because that's their main specialty. That's how plasmas have been defined in the past. So Langmuir was the first to define a plasma, and it was, of course, for a gaseous one. One in a cathode ray tube, I assume. If you go beyond the gas phase and you, for example, consider a solid metal, and you begin to investigate how these particles inside this metal behave, you will begin to see certain parallels with the gaseous plasma. And so there it becomes interesting, but at the same time confusing, of course, for many people to see this parallel and at the same time be able to tell also the difference. So if you call a metal a plasma, why do you call it a plasma exactly? And why is it different also from the gaseous plasma? And there you, of course, have to consider many subtleties, which are, let's say, in old times, when they didn't know about too much about quantum mechanics yet, they also had some ideas about what metals could do. And perhaps they also had some ideas about plasmas, because before the word plasma was invented, there were some experiments already with plasmas. Just lightning is a type of plasma. People know it already for ages. You can, of course, have some models for this, but from the moment you get into quantum mechanics, then you really begin to see that there are some very interesting similarities, but also differences between this solid state, a liquid state, and gaseous state plasmas.
It seems to me like the biggest and most important and obvious one is that liquids and solids are essentially incompressible, right? Compared to a gas, for instance, right?
Well,
And that would have huge consequences, right?
Many astrophysicists will probably disagree with you because then you can get to black holes and things like that.
Well, those are all based on ideal gas laws, from what I can tell.
I have actually no idea, but if we don't go to these extreme cases of matter yet, then it is a good approximation to say that indeed, at least in our environment, gases are very compressible, while liquids and solids are almost not compressible in their density. They remain quite nicely organized in density, no matter what happens.
But the black holes are a great example, and white dwarfs and these ultra-compact states of matter are a great example of how a confusion, if incorrect, right? If we assume that the plasmas are gases, but in fact they're more liquid-like, or even solid-like, then you don't end up with theoretical conclusions like black holes or white dwarfs. You have to search for a different route, a different mechanism to explain the like all we have in astronomy is light from the stars. So we're trying to interpret it based on our understanding of how light is created, and you could find yourself very confused very fast.
Okay, so that seems like maybe it's most applicable in terms of cosmology, right? Like in context of this conversation, in context of the conference that we're hosting, it seems like the place that all of this centers around is if you assume that plasma can only be this highly energetic gaseous form of matter, you run the risk of looking out onto the worlds to places that you can't actually visit and put into a test tube or some kind of experimental apparatus and make terrible, terrible mistakes about their very nature. Is that fair?
I think so.
Partly. I would say only partly, in the sense that there is a lot you can do in the lab
Nice.
in our planet, at earthly laboratories. For example, the reason why I actually got into this research, the reason why I met Pierre-Marie Robitaille, why I got acquainted with his model about the liquid sun, is because of my experimental work that I did in Ghent University during my PhD. So I was working there on plasmas in contact with liquids, and also a bit plasmas generated inside the liquid phase. Now, my research was mostly about plasma generation inside bubbles, but it's very related also to this topic of direct plasma generation inside the liquid phase. It is possible. You can generate, let's say, lightning underwater, or in any liquid you can think of.
Is that a gaseous kind of plasma still? Is it turning into little bubbles first?
So that's the core question, I think, in this research. You have, since I think 1 century ago, two mechanisms that have been proposed, two main mechanisms that have been proposed in this light. So first, you have the bubble mechanism, which says that first you have a gas phase which is being formed or maybe already present inside liquid phase. And in this gas phase, you will generate the plasma. And then the second mechanism, which is called the electronic mechanism, that one says that you have some electronic processes going on in the liquid phase without any low density region being formed or being present in advance. And so physicists were already proposing and contrasting these two mechanisms with each other, I think in the 1930s. At least that's as early as my literature study went back on this topic. But yeah, the weird thing that I saw was that when I was doing my research, which was, let's say, 2010 and later, 2009 it started, then I saw that many of the contemporary physicists were favoring the bubble mechanism over the electronic mechanism, simply because they couldn't imagine an electron avalanche, which is typically the initiating process for generating a plasma in the gas phase. They couldn't imagine such an electron avalanche to emerge in the liquid phase because your particles there are too densely packed on each other. So their reasoning was as follows. An electron avalanche is basically starting with one electron, which can be from cosmic radiation or just, let's say, a lost electron somewhere, that you have in the gas phase, which is being accelerated in an electrical field that you apply. Then this electron will accelerate towards a certain energy, and up to the moment that it has enough energy to ionize one of the particles in your gas. And from the moment you have this ionization energy, your electron can ionize this particle. And what does ionization mean? It means that your particle that is being ionized splits up in an ionic core, the heavy one, and an electron. So you have, instead of one electron, you have now two electrons. And so this process can continue. All these electrons can accelerate in this electric field as long as this electric field exists, and as long as your mean free path of your electrons is large enough. So that means if your gas particles are far enough from each other relative to the strength of the electric field to accelerate to the ionization energy before the electron collides.
So there's some aspect of this process that has to do with density, which is
Exactly.
that why people have always treated liquid plasmas as being somehow either impossible or a different phenomenon altogether, because there isn't this kind of rarefaction?
If you mean with people, plasma physicists of a certain specific field, then yes, but certainly not all of them. So that's one of the very funny things that I discovered during my PhD, and quite at the end of it, by the way, because I always assumed that the theoretical scientists were already realizing this, that you have two fields which are very much connected with each other in topic, but very isolated if you see it in practice, like how universities and academia is structured. The one is what they call low temperature plasma, typically, where you investigate plasmas being generated by means of electrical fields, by means of voltage, some electrical potential between two electrodes. Or sometimes it's just at one electrode. You can have, for example, at a very sharp pin electrode, if you put a very high potential, electrical potential applied to it, relative to the environment, then you can have corona discharge, which is just like a little lightning, you could say, a very soft lightning, which is connected to this pin tip of the electrode. Why? Because the electrical field at this pin tip is extremely high. If you apply a sufficient voltage to this pin, it's always at the sharp points that you will have this highest electrical field where your particles your electrons can accelerate towards these ionization energies. So this is what I would call voltage-induced plasma. And then you have next to that another field, which everybody is aware of. It's laser physics, where you can do the same. You can fire a laser and focus it somewhere in the gas phase, where you can also ionize a gas. You can do the same in the liquid phase. So as you already know, we can generate a plasma in the liquid phase. You can do this with this submerged electrode. So for example, a pin electrode positioned relative to a plate electrode. Even the plate electrodes is not necessarily part of this. It's not necessary to create a plasma. You can also have corona discharge, so this little lightning, soft lightning, in the liquid phase, just as in the gas phase. And then you can create it also with a laser. The funny part is that
how does that work with the laser?
It depends on your laser. It depends on the frequency. So with a laser, as you know, a laser is composed of photons. And depending on the energy of the photon, which is connected to its wavelength, you can have direct ionization of one species in the liquid phase. So let's say you have a water molecule. If you're or let's say in the gas phase, that's maybe easier to imagine. In the gas phase, you have a water molecule which is nicely isolated from the rest of the water molecules. If you fire a laser on your water molecule, and if your photon that is interacting with your water molecule if it has a sufficient energy, namely an energy of the ionization energy or higher, then it can ionize your water molecule. If it does not have this energy, then you can ionize your water molecule with a two-step, or let's say a multi-photon process, where you combine two photons or more photons together to get this energy and ionize your water molecule. But to have that, you need to have a very high intensity of the laser relative to its frequency. So that's where quantum mechanics comes into play for a bit. You have this quantized energy of photons. The same story goes also to the liquid phase. You can make the same reasoning there, but the situation is there, of course, a little bit more complex because your water molecules are not isolated anymore. They're a bit surrounded, not a bit surrounded, they're surrounded everywhere by other water molecules. So this will influence their ionization energy and not just make them a molecule anymore. They will actually be slightly split between an ion and an ion in the liquid phase. So, of course, this will influence the whole story a bit, but the principle remains the same. You need a certain energy to ionize something that is actually already slightly ionized, you could say. And there you see where the story becomes very interesting. Let's go back to the metal. Is your metal ionized?
I mean, right, not by convention, right? Because like ionization in convention is phase dependent, right? Like I don't think you can have an ionized solid by convention. Is that true?
I'm not entirely sure about what most so convention means what most physicists would say.
Like I guess
I think
convention
here,
is kind of what they say in the textbook. Like would the textbook tell you that it's possible to have an ionized metal? I don't.
You can have ions in a solution.
Sure.
But you don't usually, the phrase just isn't usually applied to delocalized electrons inside of a solid for whatever reason.
Yeah.
all right, it depends, I think, also a bit on the metal itself, but you can imagine you have solids which are ionized. Salt, for example. That one is a very clear example of an ion. It's hanging together with ionic bonds. Why? Because if you zoom in on one atom, it very surely has a net charge compared to the ion next to it, which has typically the opposite net charge, negative or positive. So, is
and
your salt
inside
a plasma because it's ionized?
Wait, say that again?
Is your salt a plasma because it's ionized in this way? So you see where I'm going? If you limit your plasma definition to the gas phase and you say like it's just an ionized gas, then if you want to get your plasma definition towards the solid state, what kind of characteristics does your plasma need to have to call it a plasma? Ionization can mean many things. So for example, you can imagine this ionic state of your salt to also occur in the gas phase, but that doesn't mean that you will have a similar kind of plasma than the one you typically have in the gas phase. So here comes a little, I would say, a confusing factor in this typical definition of plasma is the fourth state of matter. The fourth state of matter as above the gas phase, where you have instead of just neutral gas particles, you have these ions, electrons, and perhaps some other things. Probably also neutral particles very often is the case in at least the laboratory plasmas. Okay, let's start with this fourth state of matter again. If you have if you consider again this stepwise motion from solid to liquid to gas to plasma, are all of these steps similar? That's the first question to ask.
Each step seems like it increases net motion. It kind of increases the ability of each atom in the lattice to move. When you have a solid, everything is held together by some kind of bond that is restricting motion. Then as you move to liquid,
it's almost like a electrostatic matrix in the case of the ionic solid.
Yeah, it's like it seems like it's about degrees of freedom and how permissive
Exactly.
the bulk is.
Yes. So thermodynamically, they will also typically describe this in terms of degrees of freedom, that you will get more degrees of freedom from the solid state to the gas to the liquid state, because their rotational motions are more possible. You have liberation in liquids, which is like a limited rotation, and this is typically not the case in the solid state. You can have, of course, depending on what type of solid you have, molecular ones, you might have something similar, but let's consider these complexities for another time. But in general, you're going to consider your material as a bunch of particles that gets more free to move from the solid state to the liquid state to the gas state. Can you still say the same about the transition from the gas state to the plasma state?
Well, it seems like the transition to the plasma state is not necessarily that the molecules themselves have more degrees of freedom, it's that the parts of the molecules have more degrees of freedom.
Yes.
Or just that it's conductive.
But that's kind of what it means for the different parts of the atom to have different degrees of freedom, right? Because like if we treat conduction as being the motion of the surface of the atom relative
But
to...
it's cohesive, that's my point. It's uniform. It's actually quite restricted and patterned.
Inside a plasma too? Like it... Because you can...
Inside of like a plasmatic liquid or something, right? Or
Like...
inside of a metal, for instance.
Well, but hold on. We're still at the point where we're like liquid, solid, gas, plasma. And I'm
Yes.
like, the transition between liquid, solid, and gas seems to be degrees of freedom of the molecule, of the atom.
Yeah.
And then when you hit plasma, it's like, it's a different kind of degree of freedom. It's different in kind because you're talking about a degree of freedom that is philosophically separate.
The problem is treating electrons like material objects, ultimately, right? You can't just move these things around and still stay rational. Like, the electron is not a blob of material. That's why we kind of cringed when Patrick pointed out that they're treated like bowling balls earlier, because nobody really thinks they are. So, I mean, it's going to be hard to make sense of any of this without a material understanding of what electricity is, I think, unfortunately.
But even if you go a step back, and you look at them as billiard balls, then even you get there a contradiction, or at least a confusion. So you're completely right to say like this is to simplify it, but let's do the simplified reasoning first and see whether that already works. And there you see that you get a very clear answer with just high school physics. What is the transition from solid to liquid? It's a phase transition, classical phase transition. What is a classical phase transition? How did we learn in high school how it differs from other transitions that we know in science? What kind of other transitions do we know in science? Chemical transitions. What is the difference between the physical process and the chemical process? And there you have the answer. Physical process, your particles do not change in type and do not change in number. Your collection of particles is going to remain the same in type, but they will move towards each other, relative to each other, in a different way. Solid, liquid, gas. When you go to a plasma, that's absolutely not true anymore. You will break bonds. You will at least break the bond, if you can call it that way, between the electron and the ion. So it's actually chemistry that you have there.
I like that.
And there is even a second thing that you can consider with this bowling ball model, and that is this solid, liquid, and gaseous state are what is in science sometimes called coexistent. So you can, for example, have at the same time an ice cube laying in water, and both materials are located in a different place. You can very clearly see this is the ice cube, this is the water, and then, for example, the water evaporating at some point, the vapor and the liquid phase are in equilibrium with each other. They can exist at the same conditions, and you can very clearly see a boundary between them.
This is starting to sound like the surface of the sun.
There you get towards this topic of the surface of the sun. Now, what do we have if we go from a gas towards a gaseous plasma? Do you still have such a surface? No, not at all. They mix together so easily. So this coexistent, as defined by Gibbs, works for solid, liquid, and gas, but not for plasma in this sequence of materials. So there you have also, just based on this bowling ball model, you can say the bowling balls begins to mix with each other, or they stay together in one system, ice cube system versus the water system, and so on. You see this is a source of confusion from a physical point of view. Why would you still call plasma a fourth state of matter if it already begins to go wrong there, thermodynamically speaking, without even concluding any quantum mechanics? Thermodynamically speaking, you already see some contradictions popping up. So maybe we should change this definition of plasma relative to this fourth state of matter definition. And then again, towards this ionized gas, you also have a problem there because not, as we already said, not all plasmas are gaseous, but also not all plasmas need to be ionized. If you consider, for example, this metal and you want to call it a plasma, can you really call it ionized, like it has been ionized? Because typically what's happening when you ionize something is you need a certain energy to kick the electron out of the atom. And in a metal, it actually just happens like that, automatically, quantum mechanically.
I got a stupid question. In a metal, is the electron treated to be completely delocalized even before a current is applied to it?
Well, there you get, of course, the influence of temperature will there be very important, but there you get a very interesting answer. In general, I would say yes. You don't need to have any, in let's say, standard conditions, not like 0 Kelvin or very, very specific exotic conditions. As long as you have a little bit of a temperature, your electrons will be easily delocalized. In a metal, as you know, you have or as you don't know, if you consider solid state physics, you have this Fermi level model of a metal, where if you have a little bit of temperature in your metal, your electrons can, or normally at 0 Kelvin, at the absolute zero, they are, let's say, what is the best way to say it in English? They are filling up all these levels up to the Fermi level. The Fermi level is defined by the level to where all these electrons will be filled up. And then from the moment you have a little bit of energy that you add to this collection of electrons, which is typically heat, temperature, then some of your electrons will have a higher energy than the normal level they would be in. So they can jump over this Fermi level, and that's typically where you can have conductive current. for a metal, you don't need so much. You just need a little bit of a temperature. For a semiconductor, you need to have a temperature which is high enough for particles to cross a gap of forbidden energy, let's say. All your electrons are normally located on a certain energy level below the Fermi level. And then if your energy is high enough, for example, you shoot some photons towards your material, or you have a sufficiently high energy to cross this gap, then your electrons can jump from the valence band to the conduction band, and then you also have electrical current. So this is...
Can I ask another stupid question?
Of course.
Are these this is just the valence electron of the atom? Are there other electrons involved in bonding the lattice together?
For as far as I know, all of you have core electrons, which I guess are typically not considered with the valence electrons. So yes, but I'm actually not sure about the conventional definition, whether these are also valence in certain way, in a certain sense, or not.
What are you? Why are you asking? Because I think you're trying to drive to a point. What's the?
No, it's just something I've been meaning to clarify for some time. I think I've heard Pierre talk about before in his model of the liquid metallic hydrogen that some of the electrons are involved in bonding the lattice together, and some of them are these conducting band electrons.
Actually, maybe I should correct myself. The core electrons typically do not take part in electrical bonding, in chemical bonding. But you can have circumstances where they are excited from deep core states towards the conduction band. But so typically they just take part as the cloud around the core of your ion. If your ion is one of these higher charged types of ions. So with hydrogen, you don't have to consider this, of course. You only have typically one proton in the core. Otherwise, you wouldn't call it hydrogen.
I guess that makes sense, yeah.
And then only one electron that is typically taking part in bonding. But so if you have more complex ions, then yeah.
Yeah, I just always I always imagined that there was like in so much as an electron is some sort of patterned motion of the surface of the atoms that's conducting from one to the next, that some portions of the atomic surface would have to hold the atoms together into this lattice, and some of them perhaps, but maybe they're the same ones. I don't know.
I mean, I'm haunted right now by trying to figure out if hydrogen metal is conductive, and we're talking about a core with just this minimum of like material on the outside of it. They must be involved both in bonding and in conduction. There's no other way of thinking about it, right? Like it has to be somehow like each atom is knotted into the next one, and there's some kind of cohesive motion that ties like electrical conductivity into the next one.
Yes, and that's what they call in textbooks the metallic bond, whatever that may be. So, yeah, maybe here it's good to.
It's really funny, actually, as we're talking about this, I'm like Googling around and trying to find stuff. And it's amusing because when you start to ask these questions, the diagrams and the explanations are given with this, Bohr model of the atom with these little electron bowling balls. It seems reminiscent of a question that you ask and you realize that there's some kind of model that's more or less functional, more or less popular, but there isn't something that's easily accessible that actually offers an intuitive frame for thinking about these things. Because, I mean, on some level, they're esoteric questions. Like, I don't know how many people are sitting around wondering, like, what makes a plasma versus what doesn't make a plasma. Like, I think that that's a fairly small number of people you can gather in a room. But it is interesting that the question is so unanswered that it hasn't filtered into common wisdom. And I think that that's always really interesting when you look at some scientific question, you start asking and you're like, oh, that's weird. Like all of the diagrams and answers are extremely rudimentary models that we know not to be accurate. And that's just like kind of where it stops.
I think they're accurate. They're just not physical models, ultimately. They're like accounting models.
Realistic, maybe? Like, if we do we demand realism from our models? Is that a fair expectation?
I demand photorealism.
Yeah.
I think that there you get to the philosophical area, yeah?
Mm.
Do you want to consider all of this in the context of realism, or do you want to consider it in the context of idealism? Because many of these models are also said by many of the proponents of them to be idealizations. You will never have this in reality because nothing in reality is perfect.
That's true, but I think that it's enough to just demand that it is more true than the last one. Like, you'll never get to the end, right? It's an asymptotic curve, and so you should just attempt to each next
You
step.
should aim for realism, I suppose.
Yeah, well, because if you're not aiming for realism, what are you aiming for? You're just kind of like, well, this is a convenient picture and we can move on. And like, yeah, it is convenient, but convenience should not be the goal of science.
I think that's a whole different discussion, of course. I think a very important one. But yeah.
Well, I think
many people there have different opinion.
I think that it's related because this is such an esoteric topic, right? Like, because I always try to think of somebody wandering into this conversation from the street. And even my technical friends, like my dad's an electrical engineer, we spend time dealing with people that are like architects of semiconductor factories and computer chips, and even for them these are kind of esoteric questions, because for the engineering mind, the models that we have are sufficiently convenient that there's not really a further need. And so when I go into one of these conversations, I'm always trying to figure out, like, why is this necessary to resolve? Like, what damage is caused by the fact that you are coming into a conversation and, you know, this is, can you see this?
It's slightly off the screen.
Yeah, like, I'll try to pull this up I'll make a time point, but I'm like, right? I mean, it's just like, it's basically just the Bohr model of the atom that's telling you about, like, the way that the electrons interact with each other. And I'm like, I think that there's something fundamentally limiting about that. And I think that if we rely on convenient models for being able to think about esoteric questions about matter, it prevents us from being able to solve the next level of questions and also to make a realistic map of what nature actually looks like. Because, like Shiloh said, we have stories of cosmology, we have stories of the universe that rely on us being able to hold in our minds a model of what the word plasma means. And if that isn't easily accessible, if you have to dig and like go through all of these different processes to even begin to understand it, I think that that's really bad. I think that's bad for science. I think that's bad for progress. I think that's bad for philosophy. And it should be more accessible on the surface, that there is a debate about what this is, that the nature is not yet known, and that we must figure it out, because if we don't, we're screwed.
I think one of the big mistakes made nowadays in education is exactly that. This is missing. This dialogue is missing about we're not there yet. Okay. Of course, it is there on the surface. Like, we're still working on some things in science. But if you look at the present day curriculum from whatever university, typically you will have, and also schools, typically you will have textbooks full of models which are being considered to be quite final, at least in their rudimentary form, but this is the final end product, and this is what you have to work with. There is almost never some sideline disclaimer saying, like, be careful with this model, maybe it might not be fully correct. Typically, it's not even implied in the textbook. It's more like, learn this, make sure you can repeat it on the exam, and better also explain it in a way that we think you can understand also what this model means.
Mm. Well,
But so in the end, yeah, it's like very limiting in how people think about these models. Yeah.
Hey guys, quick interruption. Remember, this project is entirely supported by you, the listener, which means we work directly for you. But we need you to consider giving as little as 75 cents a week to make sure that we can continue to put our time and effort into this project with the full might of our attention, and we are not distracted trying to work strange odd jobs making it happen. So come over and check out patreon.com/DemystifySci and enjoy the rest of the conversation.
I wonder if you would agree with the statement that plasma is not a phase of matter, plasma is a state of matter, and that state is defined by conduction.
No.
Okay. Damn.
But close to what I would expand the definition to. It's closer already than the conventional definition. But I do agree for sure that it's better to consider plasma as a state, but not of matter necessarily. Of course, it's of matter, but it's a higher order state, in the sense that I would define it not as an aggregate state of matter, one of the three fundamental aggregate states, for example, the solid, liquid, and gas states, because these are also states of matter.
Aren't
It
they
is a
better?
state of-
Those are kind of better understood as phases, it would seem like to me. Like,
How do you-
state's
how do
kind
you
of
define-
confusing. Like, a state can be anything, but a phase is a specific concept that has to do with the actual atomic positioning and degrees of freedom and stuff like that. But I think the critical part, what Nastia said, was that it's about conduction, the transformation into a conductive state.
But even there, I would say it's the conductive part is not necessary. So you can even have a broader definition of plasmas that do not conduct.
Okay, that's not crazy, but that's wild. Explain. Lay this out.
Yeah, what's
for
an
us.
example of that?
What is conduction? Let's start with that one. Conduction is typically in let's say the general case of gaseous plasmas, the conduction is done by the charged particles, so the electrons as well as the ions, but the electrons are way more mobile, so they are typically more influential with the conductive part. So if you apply an electrical field, obviously both the ions and the electrons will be accelerated by this field in opposite directions, but the electrons are faster or more mobile, so they are the ones which will move the fastest towards the direction that they're being accelerated in. In a liquid phase, you can also have conduction, but then it will be ions. So let's not consider them metallic liquids for now, but if you have an electrolyte, for example, water with some salt dissolved into it, you can have some conduction inside this liquid by the ions moving through the liquid phase. Also according to the electrical field that you have applied. There you can still say, like, okay, if we consider also this electrolyte type of plasma, which I also completely agree with, then what if we just cancel the electrical fields? Can we still call it a plasma or not? The same with a metal. You have a metal, you apply an electrical field, you have conduction. Do you get rid of the electrical field? You don't have conduction anymore.
Well, it's the ability to host conduction, I suppose. It's actually a transition to a state that is able to conduct.
Which is the transition? Sorry.
The defining feature of what makes a plasma a plasma. Like, what is the defining feature of that state of these materials?
So in that frame, you would treat the water with ions dissolved in it not as a plasma until you add the current, and
No, no,
then
no.
it becomes.
No. It's defined by its ability to.
So it's like it has like its latent ability to conduct is what defines whether or not it is a plasma.
Transformation into that ability.
Okay, so plasma is matter that is capable of conducting when in the right condition.
You are getting very, very close to the, let's say, more official definition that you can sometimes find in specialized literature. So this ability of being able to conduct in the state where it does not occur, where there is no electrical field, how do you characterize that ability? That is the question here. How can you translate this conduction towards a more static, static characteristic? If you dig deeper into the literature and you go beyond these definitions of, oh, plasma is an ionized gas, plasma is the fourth state of matter, then sometimes you get towards a tripartite, I don't know how to pronounce the English word, tripartite, I guess. You get a tripartite definition of plasma of three characteristics. And the first one already includes a bit this ability that you're talking about. It's called quasi-neutrality. What does that mean? The word is composed of two sections, of course. The neutrality. It means that if you look at the plasma from afar, and you, let's say, cut out a little region from this plasma, typically, you have exceptions, but typically, your plasma will be neutral all over this region, macroscopically speaking.
Like there's
That's
not some place where all the electrons are bunched up and all the ions are bunched up or something like that.
Typically not. I would say it is not a perfect characteristic because that's typically what's occurring inside the bulk of the plasma. But if you begin to look at boundaries, then for sure you can have regions where you have a space charge. So typically that's when you place a solid or a liquid, like a droplet, inside the plasma. Then you will have the electrons going towards this surface of this solid or liquid faster than the ions because they're more mobile. They're 1,000 times lighter than the ions, so they're more mobile, and they will end up at the surface first, so forming typically that's like the standard story, forming a negatively charged layer at the surface, and then only afterwards the ions will follow, and this is called the plasma sheet. You will have a certain positively charged region above the surface of this liquid or solid, which is called the plasma sheet, and then that transitions towards towards the plasma, towards the neutral region, and then towards the liquid, of course, towards the liquid bulk. And if you actually zoom in a little bit better, then you will see you will always have a region, a space charge, which is positive and one which is negative. So you call it an electrical double layer. And if you're into the science of liquids, you will see that this electrical double layer is a term that also comes back in electrolytes in the liquid phase. And so again, you have a characteristic that is very, very...
Wait, so dissolved ions are considered a double layer?
In a sense, you could say so, because if you go to the second characteristic of what is a plasma, the physicists call it Debye screening or Debye shielding. What does that mean? That it means that around every ion, typically let's consider the positively charged ions in the plasma gas phase, or even in the liquid phase. You have, for example, in the liquid phase, water, for example, which is dissolving some salt. So we consider now positively charged ion from the salt in this liquid. What will happen? you will have in the direct surroundings of your ion a very strong field because of its positive charge, attracting negative charge. So this can be negative particles from its surroundings or polarized molecules, polarized particles from its surroundings. In the liquid phase, water, for example, is a very polarized molecule, can kind of get attracted partly with one of its sides. So you have the hydrogen, or the two hydrogens, which are more positively charged than the oxygen, which is more negatively charged. So in this case, the oxygen would be attracted towards this positive ion and would try to cancel its charge. And you can do this with several water molecules at the same time. And this is called de Beer shielding. So it's trying to cancel the charge from this ion with whatever you have in the environment of this ion. And your electrical field, without these particles, without this environment, would drop down with the distance way, way slower than if you have these particles trying to shield it. And then they formulate what they call a de Beer length, which is the length over which this field is decreasing with a factor of 1 divided by e from the exponential function. So here we have another very important attribute from plasmas, namely that if you go and zoom in on what is happening on the microscopic scale, and we actually try to translate this quasi-neutrality into the microscopical part, then you see what this quasi is coming from. It is neutral macroscopically speaking, but from the moment you zoom in, it's actually not neutral anymore. You have very clearly resolved some positive charges, some negative charges, and the way that they behave in the direct neighborhood of each other, that's what this de Beer shielding is, and that's the second characteristic of plasmas according to this tripartite definition. That's a static feature, I would say. It is something that is happening when you can actually take a picture of what is happening there and say, like, okay, we can see that the B is shielding here because this positive particle is surrounded directly by negative charges from either polarized molecule or from negatively charged particles. So in the gas phase, this could be actually the positive charge, the ion, is surrounded by the electrons somehow. And then you can begin to discuss whether these electrons are delocalized or not. Then you get more into quantum mechanics. But in general, it doesn't matter whether you're talking here about electrons or ions or whatever type of negatively charged particle.
What's number 3? Sorry, what's number 3?
Did we cover what number? So So the first one is quasi-neutrality. What's the second one in short form?
The Beer shielding.
Local charge, like separation of charge locally.
I see. Okay.
Yes.
And so what's number 3?
Or Coulomb screening, you could also call it. The third one is one way to say it is plasma oscillations. Another way to say it is plasmons, where plasma oscillations are a little bit, let's say, more macroscopic in their definition. Forget for a moment about the particle picture, the billiard ball picture of your material, and think again in terms of this quasi-neutrality. So I told you if you take a region out of this plasma and you look at it from afar, it should be neutral. But what would happen if you disturb it with a specific charge? You bring some charged particle in the neighborhood of this plasma, or you inject something charged, whatever it is, a charged particle, a charged droplet, you bring it inside the plasma. What will happen compared to, for example, a neutral gas, where you don't have all of this quasi-neutrality? the plasma will react on it. And if you have, for example, a oscillating disturbance that you bring close to the plasma or inside the plasma, you will create a wave. And this you can call a charge density oscillation, for example. So you have a charge density because of the disturbance. How do you have to mention this? Let's go back to your picture of the metal, for example, or you can even apply this to a gaseous plasma. But now consider your ions, your positive ions, the ionic cores in the case of the metal. Consider them to be blurred out, smeared out into space. They are a positive background of your material, whether it is a solid or a gas, doesn't matter. You just do not resolve them anymore. It's like a smeared out material, just a model, of course. And your electrons, that's the one we're focusing on now. If your electrons are in equilibrium and you don't disturb your material, they will be, if you consider them as billiard balls or as point charges, they will be located in your blurry background of positive charge. They will be located exactly at the same distance from each neighbor in such a way that, in case you don't have any kinetic energy, no heat, it's 0 Kelvin, they will be feeling each other's charge, of course, but they want to stay away from each other as much as possible because all of them are opposite, the same charge, so they repulse each other. Now, of course, when you add heat, this picture is disturbed, but still, on average, you will see that if you cut out a little region out of this material, you should, in principle, have a neutrality in your little region. Of course, if your region is very small, then this does not count anymore. But your electrons will cancel out the background as much as they can. Even if they have energy, doesn't matter. But if you now bring a disturbance into this plasma or in the neighborhood of this plasma by, for example, oscillating the current or the potential or the field over this plasma region, then your electrons will move collectively from one place to another. And you can imagine this horizontally, vertically, in the z coordinates, x, y, z, doesn't matter. You can imagine that your electrons are moved, pushed at one moment one side, and then from the moment your field is moving back, or you release the field, and the field is gone, they move back, and you have a wave inside your material of electrons. There, if you will consider this wave and you want to describe it mathematically, you have to consider at some points that your material is not neutral anymore in certain areas. It will be positively charged, the space charge. It will be a positive space charge where the electrons are absent, and where there are too many electrons together, pressed together, you will have more of a negative space charge because the background does not cancel them out anymore because it doesn't move. And so this waves that you can create inside the material, you can describe them quantum mechanically, mathematically, in such a way that takes into account how many electrons you have per atom or per ion that is in your material. And similar to how you define a phonon, and we can go back to this later, what is a phonon? Similar to a wave that you have in a material of ions or of atoms, you can define such a wave inside your electron gas, your charged gas. That's called a plasma.
It sounds kind of a little bit. It sounds a little bit like an antenna system to me.
Yes.
Where you have this oscillating charge at some predictable wavelength, and the light that emitted or received is sort of corresponds to this.
And of course, I explain it in this way because that's the more simple way to explain it. But there certainly is there are more complex situations where it's not just one wavelength, one oscillation, and it's multiple oscillations superposed on each other, a way more complex signal. And then you get, of course, into mathematical descriptions of how you can describe all of these things. But if you quantum mechanically try to define the most basic waves that you can create in this way, the ones with the lowest energy for a certain wavelength, for a certain frequency, then you get this particle or quasi-particle that they call the plasmon. Or in the case of neutral particles, the phonon.
Well, so to call it a particle is to call it an activity. Is that fair to say, right? Because I mean, like the particle, even in quantum, the standard model is not an object. It's a zone of motion or influence or action. And so when we say that the plasmon is a particle or the phonon is a particle, like is what we're saying that there's some kind of activity that the material is capable of producing or undergoing or experiencing? Like, is that?
Well, we just had a conversation yesterday with an academic physicist, and I was actually trying to explain this to Boyer last night at the jam that particles are more like bundles of information, right? It's like this kind of list of information about what you will observe at any given point, right? If you go to measure it, essentially. And so I think that's what you're trying to get at, is that like a particle isn't a mote of dust, right? Like a phonon isn't a mote of dust that just dances through the material. It's a instantiated acoustic wave inside of it, essentially.
Yeah, it's like does it offer us anything to think of it as a particle, right? Because like the word particle implies a surface, it implies inward extension, it implies some kind of static conception of it.
I would say it implies kind of locality. But at the same time, you have this wave-particle duality in quantum mechanics that makes it very easy for physicists to say, like, it's a wave, it's a particle, it's both, it doesn't matter. Well, of course it matters because your picture is constantly changing from the one or the other. But let's say according to the conventional picture of what is a quasi-particle, the name itself already says something about it. Quasi means almost, but not really.
How terribly confusing.
Yes, and convenient as well. So,
I mean, I think this word particle is just a disaster. Like, I think we should have like a all hands on deck. All scientists put down their tools for a weekend and make sense of this. It just seems like a disaster for everything.
Do you want to lay out your case for why you think it's a disaster?
Well, I just think that anytime that you apply motion to ideas, you start to get lost because ideas don't really move around. And the particle, being a bundle of information, isn't a physical actor that can move around. And even if it is an instantiated, localized prediction of some packet of information, moving little packets of information around sounds like what computers do in the abstract. But if you look at a computer, it's not moving anything at all. It's just voltages and, switches and so forth, right? It's an accounting way of looking at things. And I'm like, I guess my main complaint is I'm like, if physics won't do physical models for things like electrons and charge and conduction, who's going to do it? Like, who in the world could possibly give us that otherwise? If the physicists are only going to do accounting, then who's to do that job of actually making the material models for what is going on inside these materials?
I think it's a matter of resolution. So you can try to describe something rudimentarily, then zoom in further, try to make it more accurate, zoom in further, try to make it more accurate. And at some point, you might say, like, okay, we're at the limit of our capabilities. So this doesn't work anymore for now with our experimental tools. We cannot dig deeper. And I think that's a little bit where we are at the moment. That people get a bit stuck on what's happening on the more resolved scale that we cannot really test experimentally.
I'm not so sure that it's a matter of accuracy. I think that these quantitative models of particles, like the particulate conception, is plenty accurate. I just think it's a matter of whether we're willing to stop and satisfy ourselves with these quantitative descriptions of nature, or whether we want to actually have material models of nature, right? It's just really two sides. Like, I think that physics has done a great job of capturing the quantitative behavior of these systems, and it's parameterized them into these things it calls particles, which is, I think, a terrible word to use, but for whatever reason, that's what we have. I think it's totally fine, and it's accurate and predictive and all of these wonderful things. I just don't think it's complete. Like, I don't think that you have a complete understanding of a system without a material representation of what the material actors are doing inside of the situation. And in this case, it seems like it's the atom and whatever system of mediation you use for forces between atoms, which, but, and that's a whole rabbit hole that we can fall into if we want to, but the point is that they're complementary approaches to making a complete understanding of nature. You obviously need reams of data about interactions and measurements, and you need to fine tune that and fit it to quantitative models so you understand how the dynamics unfold. But it's strange to me that since, I don't know when, maybe the 17th century or 18th century, that people just stopped worrying about what the material representation of those phenomena really amounted to. And like you said, a lot of people will just say, is it a particle? Is it a wave? It doesn't matter. Like, that's my favorite one, is it doesn't matter. Who cares? And I'm like, no, it does matter, because we don't know what we're missing without it is the problem, right? If we have that complete understanding of a situation, then we can act upon it more intelligently. And if we only have a hazy representation of what's going on, we just have some accounting balances of what's happening, we might be missing some really critical pieces of the puzzle. And in some sense, I think this is what Pierre's trying to do with his approach to the stars. He's like, look, I know you guys have cobbled together all of these mathematics to accurately describe the observations you see, but you're not basing them on a material conception of reality. And Pierre sort of stops short of the atomic scale with these things. He goes into the schematic particle universe of standard physics when he gets to that level. But at the macro scale, he's pointing at the same fundamental issue, which is that we treat the stars as pieces of math. And by doing that, we might miss some really important features of how they do the things that they do, everything from fusion to how they die, right? Because, like we said at the beginning of this conversation, if you treat them like an ionized gas, well, then you can come up with all sorts of insane conclusions for what happens to a star. Like, it collapses into a black hole, or when you see a star that's really, really bright, but a star that's really, really hot, but it's also really, really dim, then the only thing you can conclude is that it's really small, right? But if you treat it like it's actually a material lattice that has optical properties that depend on the state of its lattice, in other words, that it's not an ionized gas, all of a sudden you have a whole sea of mechanisms available to you to interpret that dimness in a way that doesn't just require it to be tiny, right? So you change the theoretical landscape upon which you're willing to understand nature by holding yourself to a material conception of what's actually happening. And so a lot of this confusion about plasma, for me, seems to revolve around the schematization, or the obligate schematization of electronic properties to these particles, right? Which aren't actual material actors. They're just these packets of understanding about little elements of the system in a localized sense. So anyways, I have a hard time seeing this confusion as having any solution short of understanding what exactly an atom does to another atom during conduction. for starters. What exactly happens to an atom when it goes from a gas to a plasma? Like, what physically happens to it? I don't think that it just, like, its outer surface just pops off and magically flies away or something. Like,
I think you're getting here to a very, very interesting aspect of the whole discussion we had up to now, because that's where my question came. That's how I came to this question of, shouldn't we expand this definition of plasma? Obviously, this definition this tripartite definition that I just gave, with the quasi-neutrality, the Biot shielding, and the, let's say, plasmonic behavior of plasmas, or the plasma oscillations, that in itself is a model that in itself is has its limitations. And actually, funny part is that this definition is perhaps the one which is the most interesting to consider in what are its limitations, because with the other ones it's so obvious, in my opinion. The fourth state of matter, it doesn't work thermodynamically that well. The ionized gas picture, it's such a simplified picture, obviously. When you begin to talk about exotic states of matter, it falls apart completely. But this one, with the tripartite definition, you can actually say, like, yeah, we have exceptions on this tripartite definition even. And then you have to get to a more complex model, instead of the one that we are now trying to build to say, like, this is a plasma. And the people working with this definition very often also work in the field of non-ideal plasmas, where you can already understand in the title of the name of the field itself, they are very focused on the non-idealities. And so one of the aspects that is limiting anyway is this third part. We already talked about the first part, the quasi-neutrality. It doesn't really work for the plasma cheat. Well, plasma cheat might still be considered a type of plasma, in fact. And indeed, in non-ideal plasma physics, they will consider non-quasi-neutral plasmas, which have a net space charge. But then you can also go to the third one of this plasmons, this particles that are also waves, but are quasi, so not really particles. They are, in their essence, that they're byproduct from quantum mechanics. And in quantum mechanics, you can try to describe your system quantum mechanically in such a way that these quasi-particles, which are basically packages of energy, behave like particles. But it only works to a certain extent. If you have too many of them in your material, then your description becomes so convoluted that it breaks down. How do you have to understand this? Let's go to instead of the plasmon. Actually, we can do it with plasmon, we can do it with a phonon. It doesn't matter, but let's go to one dimension, where you just try to describe a wave in one dimensionally. So let's say x direction, like on a rope. And you have different possibilities of waves depending on the frequency. You have your atoms, these are the limits. Your atoms can move up and down, but you cannot move more than the atoms. So you can have the biggest wave in your material, with the case that your material is 1 meter long. That would be like half a wavelength, which would have like one node here and one node on the other side of the in this case node or rope, because we're working in one dimension. That would be the biggest wave you can define. What is the smallest wave that you can define? Is like where each other atom is moved up or down. And so then you say, like, okay, you can define a phonon for the one, and you can define a phonon for the other frequency or other wavelength. And that works pretty well if you keep it with such a very simplistic picture. But with the case, you put now so much of energy on your rope that it becomes so complex then this picture of your quantum mechanical picture of what your atoms can do becomes so complex that actually your material, your model of describing your energy in your material with this little, the most elementary waves that you can have, and then superposed on each other. So you might have one plasmon on another plasmon combined to this multiple wave state of your matter. You can say like multiple particle energetic state, quasi-particle energetic state. At some point, your material will not behave anymore like a rope. And that's where the plasmon picture just falls apart. Or your phonon picture falls apart. And now we can begin to talk about phase transitions. Do we still have a rope, or do we have some kind of liquids? Do we have a gas phase, maybe? And here it becomes very interesting, I think. And going back to Chilo's criticism, I think the best way to look at it is it's a model. And going beyond the idea that it's a model brings you, of course, into a more philosophical area. Is it real? Is it something that agrees with some object in reality? That's, I think, a completely different question than can we describe this system with this model in an accurate way or not? And it seems a very useful model to describe many materials. So, for example, and this is something that I find super weird, that this is not world news yet, as it were. In 2012, I discovered an article which was, the title of the article is The Phonon Theory of Liquid Thermodynamics. It's written by three collaborators, Bolmatov, Trachenko, and Braskin, if I pronounce the names in a correct way. And when I saw this article for the first time, I really had this immediate impression, like, this is something that should be taught in high school. This is something everyone should know. This is something that most likely will become common knowledge somewhere in the future in university courses on materials. What they found is that you can predict, or you can describe the specific heat of many types of liquids by means of a phonon model. And why is that special? And this is a very interesting part. Just imagine how important liquids are in our lives compared to solids and gases. You cannot say that they're less important in any way. Water is one of the most important substances on Earth, without doubt. If you look at the science of which states of aggregate states of matter have been the most investigated in the past century and up to now, or let's say, which have been, this is a better question, which have been the most described with simplistic models? The answer is definitely gases and solids, and liquids come at the end. And even if you go back to the literature on the thermodynamics of liquids in the previous century, you will find in many cases scientists just blatantly saying, like, this is way too complex for us to describe. We have no clue how liquids work. While thermodynamically, gases, simple, you can even go a century further back in time and see that they were already making all kinds of laws for gases, and then they came to the picture of ideal gas laws and the, let's say, Boltzmann picture of gases, where you have all this billiard ball, Brownian motion, all together forming this picture of like, okay, we can, with this picture, describe the specific heat of a gas. And we can measure it, we can compare it, we can compare our model with the experiment, and voila, it works. Do it for the solid state. You can do the same, but in this case, what do you use? Phonons. And in this case, just like we explained, just like I explained just with this rope, you can define these phonons in 3 dimensions. You can define how many you have, what is their energy, then define a temperature in your material, and based on that, you can fill up your energetic picture of your phonon states that you create with your mathematical model according to how your atoms are positioned in your lattice. And voila, you have a model which can predict a certain specific heat which agrees with your experiment. With liquids, there was one guy proposing it in the previous century, but basically nobody listened to him, and it became buried under all kind of other work, up to the point that some scientists in the recent years, so this Bolmatov, Trakhenko, and Braskin, came on the idea like let's work further on this guy's assumption. Who was this guy? Frenkel. And Frenkel had a very, very ingenious idea of considering liquids as solids which can only guide certain frequencies. So now you can think in terms of waves in your solid, but make your solid a little bit more fluid. What will happen? If you have a very fast frequency, a very fast motion, your atoms are going to shake just relative to each other, and that's it. Nothing like a big wave with a long wavelength. The very short ones, very short wavelengths means high frequencies. These ones you can easily guide through your liquid. Your liquid will not be able to stop them through the liquid motion. But from the moment you get to a certain wavelength, a certain threshold wavelength, then all of a sudden your wave that you're creating in your liquid dissolves in the liquid motion. And this depends on the viscosity. So Frenkel was saying this means that you have a cutoff frequency in your phonon picture of your liquid. And that's a little bit where it stopped with Frenkel. And then these guys who made this phonon theory of liquid thermodynamics said like, okay, let's apply this to a couple of liquids and see whether we can actually predict the specific heat of these liquids. And this model, for as simplistic as it is, worked like a charm. It could not only predict water, which is already a very complicated liquid, or atomic liquids, it can even describe metal liquids.
Can you relate the wave frequency to specific heat for us so that we understand why that's an important test?
Well, the reason why you can link them to each other. So specific heat, what is the specific heat? Specific heat tells you for a certain material how much the temperature will go up as a function of the energy that you put into the system. Temperature is a thermodynamic property that can be statistically described. So there you get your mathematical model. So you can link your temperature to your motion of your particles, while The heat you can link to the phonons, in the sense that every phonon has an energy and heat is energy. So from the moment...
And so the idea is that if you can accurately model the capacity of the liquid to hold these phonons, that you will be able to derive some property of the substance from its ability for the molecules to move, right? So it's basically
Makes
like
sense.
saying that like there is some discrete relationship between the motion of the molecules, and we can parameterize this in terms of these phonons in order to be able to derive the relationship between how much energy is required in order to heat the substance by like 1 degree or something.
Yes, and the very interesting part about this whole description is also that if you would make it very simplistic, you would think like, oh, specific heat is like a constant property and it doesn't change. But that's not true. It's actually temperature dependent. And this temperature dependence has even been very nicely reproduced with this model. So it's not just a number that you can reproduce from the experiment. It is a complete range of numbers. Specific heat as a function of the temperature.
Okay, so the way that we got onto this subject, though, is from the question of particle as a useful term in the sciences, right?
Yes.
And so I think that the idea here is that, you know, if the phonon is considered a quasi-particle, that doesn't necessarily it doesn't really get at the deeper thing that is being studied, which is the capacity of the substance for a specific type of motion. And you must derive that from some deeper understanding of the molecules that are in the water, based off of what their hydrogen bonding networks look like at various temperatures, what their density looks like at various temperatures. And so when we treat the phonon as a particle or as a quasi-particle, there is a deeper physical understanding that is necessary to even begin to make sense of it, which is that there's water molecules that are doing some kind of motion, that have some kind of degree of freedom that is available to them, which then gives you some emergent property that you can put a number onto. And
yes.
I think that Shiloh's opposition to the idea of particle in more fundamental, like in quantum mechanics or in some deeper physics, is that there's the sense that there's nothing underneath it. It's a mathematical construct that describes the field, but the field is not the description of a deeper thing that is in analogy the same as the water molecule is to the phonon. The field is treated as fundamental. There's nothing beneath the field except for like energy flux of some kind. And when you're like, okay, well, what is fluxing? They're like, what a stupid question. Like, it's obviously the fluxing. And you're like, but every other system requires us to have something that fluxes. And so I think that that's the thing, is that like particle is a mathematical model that allows you to derive some truth about the system, but it doesn't allow you to reach to the next level of deeper truth in the sense of what is there? Like, is there something there? Because if there isn't, then you have this crazy problem.
Well, if there isn't, then what are we doing?
Well, that's what I'm trying to say. Like, if there isn't, you arrive at this crazy question of, like, how did you build the universe out of math? Like, if there's nothing that is producing the thing that is at your detector, what the hell are you doing?
I think we should just rename particles vector bundles or
Ooh,
something
I like
that. Right? Something that gets so that everybody on the street understands that we have these chunks of information and that we've constructed these really, really accurate models of reality using these information chunks, but that's all they are. It just has this deceptive quality to it where people on the street, people at jam sessions late at nights, have a really hard time understanding that the reality of even the most accurate physics is still constructed from bundles of information, not from physical materials in motion.
Okay, and so then to go from that, the claim is that if we are to understand, like, if there's something that you can derive theoretically and mathematically from the material relationships of the water molecules to each other that gives you specific heat or something else, then there should also be something that you can derive theoretically from the relationship of the fundamental building blocks of matter that can tell you about plasmas, because this all started when we were talking about the idea that plasmas also have this oscillatory quality to them. And so if you can model the oscillatory quality of plasmas as something more than just mathematics, like if you can look at the math and then derive from that some substance that is behaving, then I think that you've reached some magnificently deep truth about the universe, which is completely missing from the sciences at this point.
I think I can try to get closer to that end goal, but I also am very confident I will, in the end, fail. Because you will always hit a barrier of understanding. But so in this case, I think one of the nice things about quasi-particles is they are honest about how illusionary they are. Elusive they are.
Illusory.
Illusory they are. Thank you. They are a wave of matter. And they're not really a particle. They are called quasi-particles for a reason, because, well, there is actually a little bit of a discussion, let's say terminological discussion in physics, whether they should be called quasi-particles or collective excitations. And maybe there you will be more satisfied if we call it a collective excitation. Because there is a difference between the strict definition of a quasi-particle and a collective excitation, in the sense that a collective excitation is, I think, a boson, and then the other one is a fermion. So, for example, an electron moving in a metal and pulling with it a certain phonon cloud, that would be a quasi-particle because it's actually a dressed particle. It is a real particle, an electron, dressed with quasi-particles, phonons. But the phonons themselves, they are called collective excitations because they're not really perfectly corresponding to a particle. They're corresponding to a bunch of particles collectively moving. And I think the basic characteristic of all of these quasi-particles is they're little parts of energy that are quantized. And that's the most important part to understand from it. But it is a quantum mechanics simplification.
Okay,
Quantum
so
mechanics itself. Yeah.
I think that the piece there that would make sense is that by analogy, like if the phonon is a quasi-particle that is a collective excitation, the collective that is being excited is, let's say, the water molecules.
Yes.
I think that it's possible, and I think that it might make more sense to start to think of the electron as also being a collective excitation of something.
You're getting towards a very interesting direction. I'm even thinking, if you there is this saying by Einstein. I think Einstein once said, because you never know with this guy, that you never understand a theory, you get used to it. And for me, I've been reading quite a bit about quasi-particles and quasi-particle physics. And when you get really deep into this stuff, and then you begin to look at subatomic physics, you might begin to ask, like, maybe this ether this light conducting substance called the ether might be still useful in describing what atoms are, electrons are, and all these things. because, okay, let's not think about the Michelson-Morley experiment for a moment, but
I think you're right, but I think we have to avoid that word too, because Michelson-Morley destroyed that word. Like, I think that you're right that that you're pointing at there must be the motion of some underlying material substrate, but like Nasti and I, we've adopted a different term for that substance because it's almost like you need subunits for the atom, essentially. And you can't use the word particle because that's been destroyed. So we like to just talk about like atomic fiber, just hypothetical subunits of the atom. So the atom is comprised, and the medium that links atoms together is comprised of some sort of fiber. We don't know, like gazillions of them. I don't know. It doesn't really matter. We don't know if they're heterogeneous or homogeneous. We don't know anything about them. We just must hypothesize that there is subunits to this material, the atom, because the atom changes shape, so it has to have subunits, right? It's the only way you can change shape. The things are vibrating constantly, and their shapes are changing, they're doing stuff. So it's really hard to have a rational conversation about any of this stuff without hypothesizing some sort of substrate. And I'm really, really avoiding the word ether because I feel like Michelson-Morley killed that for people. Like,
I have an idea. Let's call it the quasi-ether.
No.
Oh my
Problem
God.
solved.
Oh.
I'm gonna go with fiber, atomic fiber.
I mean, I think that it's worth noting that, like, Einstein gave an address at Leiden, and he's struggling with what the space-time is, and he's basically like, I think that we shouldn't let go of the ether. I think that space-time is a non-kinematic ether. And for a long time, I was like, what the hell does that mean? And then I realized that I think that what he's saying is that it's not an ether that is discrete from the atoms that are within it. And so it's like the atoms themselves have a network of communication. And so when there's something that is an excitation of the substance, like a photon, it is a thing that travels in this packet manner in between atoms, and it travels according to some radial distribution. But it's not just like shooting them out into space, into the void. It's like everything travels within a substance.
Can I say one more thing? I think that a huge piece of moving this kind of idea forward comes down to recognizing that instead of this kind of fluid, nebulous, whatever ether of Michelson-Morley, what we're talking about is something that must be structured materially in an interesting way so as to accomplish all of these otherwise magical processes, right? This substance must have structure in order to give rise to its functions. And that's something that you don't really see considered in these 18th century conceptions of ether. It's just sort of this stuff. It just does it somehow. Like, that's sort of not really part of the discussion. And I think that that's where the whole of the discussion lies in the future, actually, is how is the atom, the extensions of the atom, it's, if you want to say the medium of light and gravity and electrostatics and all of this, how is that structured, and how do those structures move in a way so as to accomplish the dynamics that we have very, very adequately described mathematically over hundreds of years at this point? That's where I think the future is, personally.
If we can get there, it's already just a question: are our experimental tools able to get there?
I think we have tons of data already. Like, I think we have all of the experimental data we need to fashion structural explanations for these phenomena. I mean, I'm not saying that it's going to be an easy task. I just think there's plenty of experimental data. Now, of course, just like with the atoms for our venerable ancestors, they couldn't see the atoms. We cannot see the subatomic fiber or whatever this whole system is constructed out of. We can't see those subunits. Maybe we won't be able to see them for 1,000 years till we have the technology to be able to really resolve structures that are so tiny. But they were still able to, through first principles, deduce that they must exist. And they even started playing with the ideas, back in Leucippus and Democritus. Like, these early atomists were arguing about how the different structures of the atom might give rise to the different material properties of substances. right? They intuited that, and it turns out to be absolutely true. And they couldn't see it. They didn't have the technology. They didn't even have. It was going to be thousands of years before they had the technology to see atoms, right? But they were able to deduce some very, very true statements about them just on first principles.
And I think that if you don't want to go that far back, you can point to Einstein again. Like, Brownian motion was not that Einstein looked through a microscope and saw atoms. He derived it from the behavior of larger particles in a solution that should have been under equilibrium. And he was like, well, there must be something else there that's causing this. And then he modeled what they were like, and that kind of gave a huge amount of ground, in addition to a bunch of other experiments, to there being truly like this atomic organization of the world. And I think that if we don't try, we end up at a dead end, because I'm always banging on about the fact that if you don't have a visual model for the thing that you're trying to do, like if you just have this kind of, like if the electron is just this like weird thing that's neither particle nor wave and nobody really understands it, and it's like mathematical and it collapses and it superposes and it's entangled, and it's like, what does that mean? What are you talking about? Like, what is happening? I refuse to believe that the foundations of reality are so irreducibly complex that there is not a way to be able to think of it in your mind in at least some simplified way.
I don't know if it's simplified personally, but certainly in a visual material representation.
Well, I think that it's simplified in some way, because it's like what Patrick was saying about the phonon, is that at some point it's so many different waves that are on top of each other that it's like it's not a rope anymore. It's not like you have this like neat sine wave that you can visualize. The motion is much more complex. The motion is much more nuanced and varied, that it's like unless you have some superb ability to reconstruct that in your mind, like for the most part, you probably have a simplification of what the motion would look like. That's my game.
How about that?
So I think one limitation you might anyway encounter at some point, I don't know whether it is in this subatomic particle description or even one step beyond it, but in the philosophy of science, there is this thing they call the underdetermination of theories. You can never have any theory. You cannot prove it. You can just have data that substantiate it, up to the point that it doesn't, if your model is having limitations. But so what if you have data, all the data that you have in the world that you begin to process, and you come to the conclusion like, oh, this model that I have of subatomic physics seems to explain everything very well. And we can then describe electrons in this way and protons in that way, and everything seems to fit. And then you have a second model which does the same, but is completely incompatible with your first model. It's just as powerful, as applicable, but it's contradicting your first model. If you don't have any reason to distinguish, to favor the one theory over the other than perhaps preferences here and there, then I think you're stuck. You don't know which model is real.
I think that you're totally right about that. And so I think that the model that you pick at that point comes down to the model that makes more sense to you. Like, I think about this in terms of metaphysics, where I think that I use the word metaphysics as being the foundational rules that you use to construct the stories that you tell about the world. And so for a mathematical physicist, the fundamental metaphysics is that everything is particles, and particles are the excitations of the underlying quantum field. And like that's where you begin. And then for somebody that has a more mechanistic metaphysics, you would say, well, there's something that is underneath that field. And then somebody else would come along and be like, okay, well, saying that there's fiber that is the thing that composes the field is insufficient for me. I want to know what the fiber is made out of. And so it's like, there's always these different levels at which you point to and where you start. But the same way that I don't think that you can have like a Buddhist and a Christian argue with each other and convince the other person that their metaphysics is the right metaphysics. It's a metaphysics that makes sense to the spirit. It's like, it's the thing that makes you look at the world and be like, this is a parsimonious description of the world. I like this description of the world. It allows me to do things that I think are good and useful in the world. Ergo, this is the one that I choose.
Can I just add that I think I've stumbled across the revelation recently that what Anastasia and I are advocating is actually atomism in the true sense of the atomists, the first atomists in ancient Greece. Like, they didn't imagine that what we call atoms today were the atoms that they were talking about. They literally just meant that material reality had to be broken down into subunits in order for action to occur, essentially. And the atom of today is actually closer to the Platonic forms sort of idea, which is just that there's these idealized activities that can be inscribed mathematically. The Platonists love mathematics, so they want to be able to like rigidly define these different activities, and they're idealized, which is in stark contrast. And the atom of today is built out of these ideas, right? It's built out of these conceptual relationships like charge and particles, mathematical particles,
Force carriers,
right? And so we're really just saying the same thing as the original atomists, which is like, well, okay, so you have like, it's actually unfortunate they didn't call the modern atom in the 18th century. It should have been called like a meta atom, not an actual atom, because they knew that it changed shape and size and stuff, so it had to have subunits. So they weren't actually talking about the ancient Greek atoms, which were the individual fibers, the irreducible like subunits of reality.
Okay, so this is actually also crazy because the reason that we moved into this realm of particles as mathematical descriptions of zones of influence was exactly because of what Shiloh's saying, which is that when Faraday was doing his work on electromagnetic induction, he was using this like Boscovich atom, which was made out of force fields that defined which atoms could bond to each other on the basis of compatible force fields, because they were unable to reconcile the fact that an atom was indestructible and indivisible, and so in collision couldn't be moving both forwards and backwards at the same time because it's inelastic. And so they were like, oh, well, they must never touch each other because there's this zone of infinite repulsion at the nucleus. And all that you're seeing is the interaction of these like outside resonances. And so Faraday stuck with that model. And as we moved through chemistry, we started talking about atoms as these little like objects, but we never really got rid of this idea that the foundation is some kind of mathematical relationship, some like resonant force field based process.
Platonic forms, man.
Platonic forms, yeah. And so I don't know. I guess the point here is that I think that there's something about the study of plasma that you're doing, which is talking about the fact that there is some capacity of substances to behave in certain ways that makes them plasma, which actually points to some deeper foundational organization of substances, which is that there is a relationship between the subunits of matter that can be set into motion that produces conduction, but that the structure is the thing that we're trying to get to. We're trying to understand what is the organization of matter that produces the capacity of conduction, even in the absence of the motive force. And that's crazy because that's this huge reframe of the entire discipline, of the way that we think about the world. And I think it strikes at something so fundamentally deep that it's almost hard to put into words?
Can I try?
Yeah.
Desperately, maybe. But I think, well, my idea of this possible link between the subatomic physics or metaphysics and my concept of plasma is that this new definition of plasma, as I want to introduce it in the plasma physics community, is very much revolving around a more holistic characteristic of matter. It's not considering one particle and another particle interacting with each other. It is considering all particles to be interacting with each other in some way that you can then describe mathematically in simplistic terms in these quasi-particles. But it has this holistic nature. And if you then begin to zoom in further...
Like holistic in that they're excitations of some common substrate. Is that what you mean?
Yes, so I'm not sure whether it's entirely correct to say that you can locally see the environment being influenced by the thing that you're describing. It is a particle in the sense that it is somewhat local, but the locality includes many particles, the real ones. And these real ones can be just as real as the quasi-particles in the sense that they might also be excitations of something. And this something, then we can try to model as well in some way and see whether it then fits with what an electron is, what an atom is in the end, what a plasma is in the end. And then I think we're getting on the right track. But again, this does not mean that we're on the right track. If it works well, that's the first part, but maybe it works well just by coincidence. So for example, when you were talking about Einstein and his Brownian motion, you can say, like, was he a genius to discover this? And okay, Einstein is known as a genius because he was having many of these insights that turned out to be very useful. But with his Brownian motion, maybe he was lucky.
Sure, why not?
And so yeah, he became not only famous for that, of course, but that one sort of amplifies this idea that if you have a lot of ideas and you put them out there and people catch on just 3 of them, then you're a genius in these 3 ideas. If you just shut your mouth and don't say anything and maybe once say something and it's wrong, then people think you're an idiot. But you see, the more you talk, the more great ideas you can have. Some of them can be coincidentally true. Others can be actually based on reasoning. And of course, there was reasoning with Einstein, but much of this reasoning is inductive. Much of this reasoning is based on luck factors because, you have to fill in the gaps. And maybe you're right, maybe you're wrong. And in the end, if you're the one who was right, then you may become famous, and that's good for your CV, even if you're posthumously finding these things out. But in the end, it becomes everything returns back to this question. I think, like, what does it mean to predict these things? How can we formulate a way to make more accurate predictions like these? Is it possible, or is it just a matter of luck and trial and error, and that's it?
I think both, personally. I think both for sure. Like, I think this is what's so wonderful about Pierre's work too, is that, a lot of the behaviors that he's describing are well predicted. They're very accurate. They're mathematically described. But when you have that material conception of reality, it allows you to reevaluate extant interpretations of those formula in a way that I think is predictive, right? If we ever make it out to a white dwarf star and we're like, holy crap, it's actually not that small after all. It just has like a disrupted lattice that changes its emissivity, and so it's just dim, right? That would be an accurate prediction of his model. But who knows when we're going to make it to a white dwarf star? Like, this might be 1,000 to 10,000 years in the future, right? So it's hard to wholly back ideas just based on their predictive powers, because it could be a really long time. The ancient atomists, right? Nobody validated their ideas for 2,500 years or whatever it was.
And I think that there needs to be a sense that we could be totally, dramatically, radically wrong. Like, I think that there's people out in the world that propose that we live in a simulation, that none of this is real, that we are simply just NPCs in some computer game. And I don't particularly like that or care for that. And I think that a lot of that set of metaphysics leads to a lot of perspectives on the world that I think aren't very useful. But I try to hold in my heart the sense that we could be totally wrong about everything. Like the things that I hold most dear, the things that I think to be the most accurate and the most parsimonious explanations of nature could be turned over if someone is able to demonstrate that they aren't the right way to see the world.
Yeah, show me the way and I'll follow you today, as Neil Young said.
I didn't know that. And I think that it's having a little bit of humility while also trying to figure out something that makes more sense is the way to go. Like, we could be
Yeah.
wrong. It's like,
I-
I think about this in terms of atoms too, where I'm like, what if we're just totally wrong about the way that matter is organized? And this is just some convenient fiction that seems really reliable and has worked, and because we can't see them, you can, if you image it, you see these little spheres, right? Like the little IBM cartoon of the like atom kid like going and like kicking a little ball. It's like
You're
that's
really just seeing like zones of influence with the little probe, right? Little
yeah,
anthem.
exactly. And so it's just like this is kind of what you said earlier, Patrick, is that you can't know the thing in itself. You can just kind of get closer or farther from it.
But you can hypothesize it, and I say we should.
I think it's a very healthy habit to have this balance between total skepticism of like we might be completely wrong, at least like this very eternal sense of doubt that you can never be certain, and at the same time the curiosity and the willingness to discover, because
yeah.
otherwise you just get stuck in infinite skepticism.
I think that it's really useful to remember that the Cartesian phrase is not "I think, therefore I am." Descartes actually wrote, "I doubt, I think, therefore I am." Doubt is at the center.
Well, listen, Patrick, I'm sure we can knock our heads around some more once we get to Portugal. So we're going to see you there very, very soon. And you are doing so much awesome work behind the scenes too to make this conference happen. And so I want to definitely give you credit for all of this work you're putting together. Not only some abstracts and helping cultivate our poster session, but you're helping get us started on our first publication as a team, right? Where we're going to actually try to recap on what's gone down at this conference after it's over and put it into a roadmap for what comes next, right? What's a better approach? And I just think that's so cool that you volunteered to do that and are taking that on. And I think it really legitimizes and orchestrates and organizes all of the effort that's going into this project, in particular this conference this summer. So
You are the quasi-particle of the Beyond the Big Bang ecosystem.
It's a nice metaphor. Yeah, I think this is with pleasure. That when you invited me for the conference, I immediately felt this sense of community coming up. Like, this is necessary. This is absolutely necessary at this point, that we as unconventional scientific thinkers become more of a group, collaborators, even though we may very much disagree on certain points and have different perspectives on many topics. And certainly, I think people on the conference will have many different ideas there, and many ideas that might also not be compatible with each other. But that doesn't necessarily break the community. That's I think part of being a community. The diversity, the intellectual diversity. And I think that's something that is undervalued at the moment in science. That they always want to go to this monolithic picture. This is it. While I see a lot of future in what we're doing in the non-standard cosmology and astrophysics. I think this event is not just going to go down in history as like a little bit of fooling around and that's it, and just for the fun of it. I think it will become historic at some point, even if we do not reach too much. At least the attempt towards the purpose that we're trying to follow, namely making this more of a community, making this more of a let's say recognized scientific subdiscipline. That's, I think, a start of something new, because for now I think it was missing.
I think that's absolutely right. I think regardless of whether we come up with the appropriate solutions for what comes next, we're modeling a way that we can proceed in the presence of very rigid and stultifying academic institutions. Every single academic we talk to, whether on camera or off camera, will tell you, oh man, like my community is such a drag. Like everybody's trying to kind of hold me back from putting these ideas out there, those ideas. Like everybody, even like very well established, like really well established scientists will tell you this stuff at dinner, right? Everybody's feeling that. And so I think just setting a cool model, speaking of models, like we're just trying to model a new way of discussing ideas and putting them out in the world. So even if all of our ideas fail, which I don't think they will, I think we have some really cool ideas being presented this summer. But even if they all fail, we're still doing something that I think is really important in terms of showing people how to do this in the future. And so that alone, I think, does make it potentially very historic and useful to the rest of future scientists everywhere.
Absolutely.
But I don't know, man. Let's put a pin in this and talk about it more in Portugal.
Sure. And if you want to know more about the plasma picture of things, the sun, and then other things in the cosmos, this is exactly what I will talk about in the conference. So my talks will be completely following this podcast's topic. So just to
Me too.
concretize it a little bit, I've developed a model which I called the multi-plasma model, which I will use for my 2 presentations in the conference. So I will use my 30 minutes of presentation for 2 presentations of 15 minutes, and each of them builds further on this plasma concept.
Very cool.
That's amazing. I'm really looking forward to it. It's going to be a fantastic weekend, and I'm so glad that you're involved and coming, and that we're going to get to see you talk.
And guys, there's a couple of, if you're listening and you want to come out to Portugal, we still have a couple of tickets left. We don't have any rooms left, but if you can make your own accommodations, we would love to see you there in Sesimbra, June 12th to 16th.
It's going to be awesome.
All right, Patrick, thank you so much for coming by.
Thanks a lot for inviting.
Yeah. Bye, everybody.